Welcome, everyone. I'm Pamela Hughes. I organize the Friends program at the Institute, and thank you for joining us, for those of you who are in Princeton on this very blustery spring day. I'm delighted to introduce today's speaker, Dalimil Mazac, Founders Circle member in the School of Natural Sciences, sponsored by Edward and Kiyomi Baird. Dalimil earned a BA in mathematics from Cambridge University in 2011 and went on to the University of Waterloo Perimeter Institute for Theoretical Physics to pursue both a master's and PhD in physics. A theoretical physicist working on various aspects of quantum field theory and quantum gravity, Dalimil is particularly interested in how theories are constrained by their internal consistency, an approach known as Bootstrap. In addition to his current membership at IAS, he's an affiliated investigator of the Simons collaboration on the non-perturbative Bootstrap. Dalimil is widely published and has given numerous conference, workshops, and departmental talks, as well as invited seminars, including most recently the CERN String Theory Seminar, East Asian Strings Webinar, NYU Physics Research Seminar, and the QFT and Geometry Online Seminar, the topic of which was Sharp Boundaries for the Swampland. I suspect that has nothing whatsoever to do with swamps as we know them, so perhaps Dalimil can say a bit more about that during the Q&A. He's received a number of awards and prizes, including the 2018 Vertuba Prize for the best thesis in theoretical physics, the Perimeter Institute PhD Award, and a Perimeter Scholars International Award, as well as junior and senior scholarships at Trinity College, Cambridge. Dalimil was also a two-time gold medalist at the International Physics Olympiads in 2007 and 2008. We're so pleased that Dalimil is here at IAS this year and will be with us for 2 more years, so we may all get to meet him in person. And pleased as well to have friends Ed and Kiyomi Baird with us today, who've provided generous support for Dalimil's membership as Founders Circle donors. Thank you, Ed and Kiyomi. So now please join me in welcoming Dalimil Mazac, who will speak with us on quantum fields and sphere packings. If you would please mute your audio. The other thing I might ask is if we could be sure that the closed captioning is on, so that if you would like to take advantage of that, you can click that button at the bottom of your screen. Okay, Dalimil, all yours.
Okay, great. Thanks for the wonderful introduction, Pam, and thank you all for coming. It's really nice to meet you. I hope you're going to have some discussions, maybe during the talk or after during the Q&A session. So related to that, I really like to encourage you to interrupt me while I talk, even and to ask questions during the talk, because it will also be useful for me to know in which direction to go, what you're most interested in. Also, I'd particularly like to thank Ed and Kiyomi Baird, who I think are with us today, for their continued support of the Institute and my membership in particular. Okay, so the talk will be about some ideas that I've been thinking about recently and for the last couple of years, which relate to quantum field theory and sphere packings, and in particular to some very interesting mathematical relation between these two concepts. But because I believe that probably most or all of you in the audience are not really expert theoretical physicists, really the main goal of the talk is to unpack the title and explain to you what are quantum fields, what is quantum field theory, and what is the sphere packing problem, and then eventually, hopefully, we'll get to the relationship that we recently uncovered in my work. All right, so let me begin by like a broad overview of why I'm a physicist, why I'm interested in physics. So really, if you keep asking questions, why is the universe the way it is, then sooner or later you're going to end up in physics, and in particular elementary particle physics. So you can think of this sort of layered structure of how we understand science, where at these various layers there are various disciplines, and of course this is a very simplified picture, but somehow the basic the basic assumptions at each layer follow from the findings of the previous layer. So, for example, sociology being the study of how societies work, or if you ask why do societies work the way they do, it's mostly because of how individuals think and interact. So it's rooted in human psychology. So that's the field that studies how the mind works. And then if you keep asking, well, why does the human mind work the way it is? Well, really at some basic level, at the molecular level in your brain, it's all about biology, how the brain cells, neurons interact with each other. So then you're forced to study biology. And then, well, why is biology the way it is? Why do cells look the way they are? Why do they interact the way they do? Again, at the deeper level, the cells consist of molecules which interact with each other, and this is the subject matter of chemistry, which studies the chemical reactions, how molecules collide and combine and decay. And then again, you can keep asking this question: why? Like why is it this particular chemical reaction that happens and not this one? And the answer is, well, all of this is a consequence of some elementary laws of physics. It's really, as I'll mention soon, it's really about how the electrons in the orbitals of atoms interact with each other electromagnetically. So in this way, in principle, you could derive all of chemistry from physics. Well, at least if you have a very powerful computer. And eventually, well, so far this chain of implications ends in elementary particle physics. So elementary particles is, in some sense, the deepest aspect of physics. We believe everything around us consists of elementary particles. And if we could only understand what are all the properties of the elementary particles and how they interact with each other, then we could go back up this chain of implications and understand, in principle, all of the world. So this is why I'm interested in physics and elementary particle physics. But of course, in practice, this is not what we do. Like nobody is hoping to explain things like love or art using properties of electrons and protons. But at least in principle, this is how things are supposed to work. But it could also be that there is something deeper than elementary particles, such as string theory. But at the moment, the experimental evidence is that well, stops at the level of elementary particles. And that's what I'll focus on today, and that's what I'm mostly thinking about. So what are elementary particles? Well, you're probably familiar with some most famous examples. So here's a picture of an atom of lithium. Actually, there are 3 electrons. So electron is an elementary particle. Electrons interact electromagnetically using another type of particle called a photon, and I'll say more about it later. And there's also a nucleus, which the nucleus itself is not quite elementary. It breaks up into smaller pieces. So for example, in the most common isotope of lithium, there are 3 protons and 4 neutrons. And in 1970s, it was discovered that not even these protons and neutrons are elementary, but they themselves consist of a triplet of even smaller particles called quarks. But this electron, quark, and photon are believed to be truly elementary, so unbreakable, or at least so far, there is no experimental evidence that they themselves can be broken apart into smaller pieces. Okay, so as I already alluded to, essentially all of chemistry, all of chemical reactions that happen in our world are consequences of the specific way that electrons interact with photons. So electrons in the orbitals of atoms interact with photons. So if you can only write down all the precise law of electrons and photons, you could explain all of chemistry and then go up this chain and maybe eventually explain everything if you're very ambitious. That brings me to the subject of quantum field theory. I'll soon say more about quantum field theory, but the reason why, what quantum field theory is the universal language of particle physics. So if you want to, say if you want to read poems, you will have to learn some language. So for example, you can learn English language, and then you can read and write poems. So in a similar way, if you want to understand particle physics, you're going to have to learn the language of quantum field theory. The subject of quantum field theory started in around 1926, shortly after the invention of quantum mechanics, and it was kind of started in a paper by these 3 gentlemen: Max Born, Heisenberg and Pascal Jordan, who were also among the founding fathers of quantum theory. But unlike many other physics disciplines, which are more or less finished, like we understand, like for example, in many cases we understand what's going on. With quantum field theory, it's not quite that. There are many, even though over the years enormous progress has been made, and in some sense quantum field theory is the most successful framework in our understanding of the world or of physics, there is still a lot we don't understand. And in some sense, most of us in the particle physics section of the School of Natural Sciences at the IS, and many other people, the main thing that we really want to understand is to understand quantum field theory at a deeper level. So that's what I work on. My goal is to understand quantum field theory at a deeper level in my research. So now let me just briefly say more about what quantum field theory is. So the central notion, as the name suggests, is the notion of a field. The most familiar one from an example of a field is the electromagnetic field. Here is a depiction of the magnetic field lines of a magnet. And you can think of a field as some kind of fluid-like substance which permeates all of space and which can depend on where exactly in space you are. It can also depend on time. Okay, so this is the notion of a field as understood by physicists. And the remarkable discovery of early 20th century is that particles and fields are essentially the same thing in some sense. Well, the precise statement is that an elementary particle is just a ripple, a wave propagating in the field. So for example, for electromagnetic field, if there are ripples formed in this fluid-like electromagnetic field, we observe these ripples as light, as particles of light, also known as photons. So here is a depiction of a torch with an electromagnetic field emanating from it, which is basically equivalent to having these point-like, photon-like particles. So, this may be slightly unfamiliar because I'm sort of alluding to the notion that particles and waves are like one and the same thing, which is quite different from our everyday experience. But that's how nature works at the microscopic level. That there is not really a big difference between particles and waves. And quantum field theory is the language which incorporates this, which really explains what it means for particle and wave to be one and the same thing. Maybe there are some questions about it. This. Okay, if not, I'll keep going. So not only that quantum field theory unifies the notion of particles and fields, but maybe more importantly, it unifies two main pillars of modern physics, namely quantum mechanics and special relativity. And in fact, the discovery or invention of quantum field theory was forced upon us by trying to combine quantum mechanics and relativity. So basically the basic idea in quantum mechanics is that things can be in multiple states at the same time with some probability. So here are some pictures of electron orbitals in a hydrogen atom, which depict the probability distribution of where an electron can be. So it can be both here and here with some probability. The brighter it is, the higher the probability. So that's the basic tenet of quantum mechanics. And on the other side, we have special relativity, which one of the basic properties of our discoveries as the part of special relativity is that nothing can travel faster than the speed of light, and that the speed of light is the same for all observers, no matter how fast you're moving. And it's really hard to combine these two sets of ideas, the quantum mechanics and relativity. We can maybe talk in the Q&A why it's so hard to combine them. And the quantum field theory came out as essentially the unique answer to this problem, to the answer to how to combine this quantum uncertainty and the precise requirement that nothing can travel faster than the speed of light. So that's, for example, the existence of particles and antiparticles is a essentially necessary mathematical consequence of combining quantum mechanics and relativity. Now, so quantum field theory is a bit of a misnomer because it's not really a precise theory. It's more like a language. It's a language in which you can, just like in English, you can write various novels, various poems. Also in quantum field theory, you can write down various models, various theories. And there is one specific model which has been well, proposed and confirmed with great experimental precision, which describes essentially everything in our universe, perhaps with the exception of gravity. And this specific quantum field theory is known as the standard model, which has to be the most inappropriately modest name in theoretical physics because it's really all over the world. Like it describes all the particles in our world and very precisely. It has not been refuted by a single experiment. It consists of a handful of particles, including the electron, photon, and the quarks that I already mentioned, a couple of others, for example, the Higgs boson, and the laws in which according to which these particles interact can be put on a T-shirt. So it's really not such a not a very complicated model, but it has some drawbacks. For example, it has free parameters, so it doesn't predict the precise masses of the particles. The masses of the particles need to be put in by hand. So it's not perfect, but it's great. Now, this theory, this standard model and quantum field theory is maybe the most successful, experimentally successful theory in the history of physics. It's in perfect agreement with experiment. One famous example is when you think about the electron. So the electron is spinning around its axis, and because it's charged, it acts a bit like a magnet. So this little current that is created creates a magnetic field, and you can try to measure, you can try to predict what is the strength of this magnet. And the strength of this little magnet, which is the electron, is called the electromagnetic moment. And you can try to compute it from quantum field theory. And you get some answer, which it can be computed to many digits of precision. Like this is about 15 digits of precision. And then you can also measure this in a lab. And what you find is a spectacular prediction. So actually these answers differ only at this, I don't know, it's like 15th decimal place or so. And they are actually compatible within the error bars. So really spectacular agreement between theory and experiment. Of course, to actually compute this from the theory is very hard, but over the years, people have gotten better and better at producing this theoretical prediction. But it's not always so easy. I mean, it's actually do the calculations in quantum field theory is very hard. And the reason it's hard is that, well, so it's somewhat easy when the elementary particles in the field theory are weakly interacting, like when they don't talk very, very strongly to each other. But that's, for example, the situation here. The electron and the photon talk to each other very, very weakly, and that's why we can do this calculation very precisely. But there is another example of the muon, which is essentially the same as an electron, just a bit heavier, well, 200 times heavier. And you can run the same experiment for you, the same calculation. And the calculation is actually much harder in this case because of the higher mass, the muon talks, well, some other particles talk to muon more strongly than to the electron. The details are a bit complicated, but it doesn't really matter. But it's very hard to produce the theoretical prediction in this case. And there are actually two theoretical predictions using different methods which disagree with each other. And very recently, at the beginning of April, new experimental results about this magnetic moment for the muon came out at Fermilab. And well, they more or less agree with one of the theoretical predictions and disagree with the other. So it's a very interesting situation. It could be because, it could be that it has to be one of the theoretical predictions is wrong, at least one of them. But if there is a real discrepancy between theory and experiment, this points to some new physics, which would be like the first big evidence for new physics beyond the standard model in many years. So people are very excited about this new experimental result that came out of Fermilab. Okay, so what I've described so far points to some great successes of quantum field theory, but also to some problems that it has. So I already mentioned that one problem is that there are these free parameters. Like for example, one day, if we come up with some ultimate theory of the universe, we would like to predict what the particle masses are. We would like to understand why it is that the muon is about 200 times heavier than the electron. But so quantum field theory is not able to do it right now. So far, all the masses and other couplings are just free adjustable parameters. It still makes infinitely many predictions, but masses are not among the predictions. So that's problem number one. Problem number two is that calculations are only possible when the particles interact weakly. So for example, for the electromagnetic moment, it's possible to compute it very precisely. And for the muon, it's much harder, which is why it's so hard to compare it to the experiment. So one would like to have a better framework where the calculations, even when the particles interact strongly, are possible. And finally, quantum field theory is not mathematically rigorous. So it means that it means that we cannot explain quantum field theory to mathematicians very well. And it's not because mathematicians are dumber than physicists. It's because mathematicians have a higher standard for what is considered true. You can start with some basic assumptions, and you want to derive the consequences in an algorithmic step-by-step manner, such that you're always sure that whatever you derive at the end is a necessary consequence of what you start with. So with quantum field theory, we don't have such a completely mathematically rigorous framework. So these are some of the problems, and well, one would like to solve these problems. And that brings me to what I'm working on. So I'm working on an approach to quantum field theory, which is simultaneously trying to address all of these three problems. And this approach is maybe in a funny way known as the bootstrap. So the bootstrap is the idea that starting from some minimal input, you can derive some far-reaching consequences. So you can like pull yourself up by your own bootstraps, starting from it's almost like contradiction. Starting from very little or nothing, you can get very high up. So the bootstrap philosophy is the following. This is a philosophy which applies not just in quantum field theory, but in other areas. But I work on it in the context of quantum field theory. So you start from some general principles, some physical principles such as that probability is always, all the probabilities sum up to 1, or that nothing can travel faster than the speed of light, principles like that. You express these in mathematical language, and in the final step, you derive some rigorous mathematical consequences from these general principles expressed in mathematical language. And what one would like to understand eventually is what are the possible solutions of this problem. Like if we write down all the, imagine we know what the basic principles are supposed to be. It's not always true we know what they are, but if we know them, then we can try to classify what are the allowed sets of laws of physics. And we can try to understand whether there could be any other universes, whether there could be a universe where muon is not 200 times, but maybe 300 times heavier than the electron. Or maybe eventually we are going to discover that the only universe, the only sets of laws of physics which are possible is our universe, which would be very intellectually satisfying. So this was nicely expressed by Albert Einstein, who said that what really interests me is whether God could have created the world any differently. In other words, whether the requirement of logical simplicity admits a margin of freedom. At the moment, we are quite far from realizing this dream, but there has been a lot of progress over the last 20 years in some specific contexts on realizing this dream. So on constraining laws of physics just from first principles. So here's an example. This slide is based on a paper by these authors. So in this example where this bootstrap philosophy works remarkably well concerns so-called critical exponents in superfluid helium. So the details don't matter, but the idea is that you can take superfluid helium and you can measure some quantities in superfluid helium, which are somewhat analogous to particle masses. So these three axes, the X, Y, and Z axis, are kind of like particle masses in a quantum field theory describing superfluid helium. And well, these quantities were experimentally measured, and it is actually a fascinating story. The measurement happened on a space shuttle, Columbia, in 1992, because Earth's gravitational field makes the measurement very difficult. So you want to take the superfluid helium up to space, to the orbit, to make the measurement. And the experimental result was between these two brown planes. So the quantities are supposed to be, according to the experiment, are supposed to be confined here. Now, the green rectangle is the result of some more traditional, it's a theory prediction, but more traditional quantum field theory. And you can see that it disagrees with the experiment. So either the older quantum field theorists made some mistake in their calculation, or there is a problem with the experiment. And finally, the little blue island is a result of the bootstrap. So the bootstrap, we just write down these axioms and we try to essentially solve for these particle masses on the X, Y, and Z, just from nothing, just starting from some first principles properties of materials like superfluid helium. And what they found is that the correct answer is confined in this very small region. Oops. And in particular, it disagrees with the experiment. So there has to be a problem with the experiment. And the correct answer was somewhere in the intersection, probably, of this green old theory green answer and the bootstrap answer. So bootstrap really works, and we are hoping that one day we'll be able to make more progress and actually, make a similar plot, but where on one axis is the electron mass, on another axis is, say, the muon mass and the tauon mass. So these are like the three basic fermions in the standard model, and maybe one day we'll be able to do that. We'll be able to say, well, there is no other way for universe to be than for the muon to be 200 times heavier than the electron, but we are certainly not there yet. Now, my work has mostly been in understanding, just with a pen and paper, these types of bounds. So this blue region in this paper from 2019 was derived using very, very, very heavy computational machinery, like on a computer. It was a simulation which ran for days. And that's, of course, it's fantastic that it works, but one would like to do better and really understand it just by pure thought, just with a pen and paper. So that's the kind of things I've been thinking about. So in a couple of years ago, I was able to provide an analytic proof for these types of bootstrap bounds on various masses, just starting from first principles. And my main interest in this is that I think eventually this will point us to some deeper, maybe geometric or some deeper understanding of what quantum field theory is. Now so that was about physics, and now in the last couple of minutes, I want to tell you how all of this is related to sphere packing. So there was I'm really turning the page. Sphere packing problem at the first sight has nothing to do with quantum field theory, but I'll try to explain to you why it does. So what is the sphere packing problem? It's not really a problem in physics, but more in pure mathematics. And the problem asks to find the densest packing of identical spheres. Now, usually normal people think of spheres as three-dimensional objects, but in mathematics, you can generalize this to arbitrary number of dimensions. So for example, the two-dimensional sphere is just a disk. And in that case, the densest packing is known. It's this so-called hexagonal lattice. You stack disks in line, and then you shift them by sort of half, by one radius in the next layer, and so on. So this is obviously the densest packing of disks in 2 dimensions, but actually surprisingly difficult to prove it rigorously. It was only proved by Toth in 1940. Now the real problem of sphere packing in 3 dimensions is even harder, but the answer is also kind of obvious. It's this phase intercubic packing, so-called, which comes about by essentially stacking layers of this hexagonal packing on top of each other, always shifted by a little bit, so that the spheres in the second layer are centered over these dips in the first layer, and so on. And it was even harder to prove mathematically that there is really nothing better than this packing. It was only done by Tom Hales in 1998. And I think it took about a couple of years to verify his proof on a computer. So it's really a tour de force. Now, as I mentioned, you can think about spheres in higher dimensions. Mathematicians are really good at generalizing notions to higher dimensions. And sphere in general dimension is just like the set of points, some distance. fixed up to some fixed distance from a center. And it turns out that the sphere packing problem can be solved also in 8 dimensions. And the solution is the so-called E8 lattice, whose specific projection is shown here. I don't think I have much time to go into the details, but I mean, it's really kind of spectacular that so far the sphere packing problem is only solved in 2, 3, 8, and 24 dimensions, and it took until 2016 when Marina Vyazovska proved that this beautiful structure known as the E8 lattice solves the sphere packing problem in 8 dimensions. So what this shows is a specific 2-dimensional projection of the 8-dimensional lattice, and the packing you get by putting the sphere centers at the vertices of this lattice. Okay, this may be getting a bit too technical, but I think it's a pretty picture to show, and the proof by Marina is really remarkable. So it's just a discussion of the sphere packing. And what we realized with my collaborators recently is that well, we were of course working on the Bootstrap approach to quantum field theory, and we stumbled upon this paper about Marina's proof of the sphere packing problem in 8 dimensions, and we realized that there are some very strong resemblances between the two things. And eventually we realized there's a perfect map. So the way she proved this was by essentially proving some optimal bounds on these packings in 8 dimensions. And these bounds can be mapped one-to-one to this type of bound on the particle masses. Like, the details are very technical, but I just want to explain the basic spirit. So there's really a perfect one-to-one map between her approach to the sphere packing problem and our approach to constraining quantum field theory. Like, it's so close that you can imagine an alternative reality where if we had known about a sphere packing problem, we could have solved it using our methods from quantum field theory, or vice versa. If Marina knew about our Bootstrap tasks in quantum field theory, she could have essentially solved our problem. But we all realized that there is this connection after all that work was done. But certainly it's a remarkable parallel or correspondence between these two approaches. The details are very mathematical, so unfortunately I don't think I can convey the full beauty of the connection, but I just wanted to state the result. And this points to a very general phenomenon, which is this rich web of connections between physics and mathematics. Really, the more we learn about physics and mathematics, the more we realize how everything is connected with everything else. And ultimately, this, in my opinion, points to the ultimate unity and simplicity of nature, that at the deepest level, elementary particles interact in some very simple ways, and we'll be able to understand them in a simple and unified manner. So I hope, well, I'd like to conclude the talk by stating that it looks like we know a lot, but there is a lot more we do not know. So things are very exciting, and I hope you enjoyed the talk, and I hope there will be some questions. Thank you.